now I would like to welcome two experts. Harry Bikas, he represents the science perspective, and Martin Schäfer, also from Siemens, but a totally different branch, who represents the industrial perspective. And Harry Bikas has a degree in mechanical engineering and aeronautics from the University of Patras in Greece. And he's a research engineer at the Lab for Manufacturing Systems and Automation at the University of Patras. And furthermore, Martin Schäfer, senior key expert, additive manufacturing at the Research and Development Department of Siemens for corporate tasks. And he's responsible for the coordination of the AM research project. It's a European project which deals with the latest trends in additive manufacturing, which means 4D hybrid production. I think this is really, really interesting. So thank you so much for coming, and please give the both experts great applause.
Thank you. Yeah, thank you very much for this warm welcome. Yeah, my name is Martin Schäfer. I'm coming from Siemens, and but today I wanted to present you a European project with my colleague Harry Bikas, and therefore the information given was quite amazing what our competences have. And yeah, but today I wanted to show or say about this project, and as was an introduction, that today we are focusing on additive manufacturing but hybrid manufacturing. That means we wanted to develop modules where we can look for and use it in one single machine or with robots or a single stage, that we use it for manufacturing and operation. So the objectives are that, as I said, we wanted to create modules, and not only high sophisticated but also very compact and also low cost, because we wanted to use it also for repair on site. So therefore we also develop sensor systems and also for the monitoring. And these solutions will be tested from these end users, that will be Siemens and also General Electric and also Global Industries. These companies stay for 3 industrial sectors. That is the power generation, the aerospace, and also the oil and gas. And therefore you heard a little bit in the previous presentation that these industries are in surroundings or environments which are very in harsh conditions. We have high temperatures, we have chemicals that are very aggressive. Our products working 24 hours a day, all the week. So we have complex parts, we have large parts, so different kind of geometries, and also that we have a lot of different kind of materials. So that are the challenges we are faced, and we try to find solutions for some of them within the project. And why 4D? You can see that, or we wanted to bring the 3D technology, the additive manufacturing technology, on the next level into industrialization. Therefore 4D, but also we have here 4 approaches. So as I said, we wanted to bring the different technologies together, the conventional, the traditional processes with the new one, with the advanced, with additive manufacturing. We want also to look at the products. We want to look at the design for the products and also for the processes. Third one is, as I said, we wanted to develop modules which are tested or implemented in machines, in one machine, or in modules which are available to also to repair things on site, means during production. So last but not least, it is a control platform what we have, because, as I said, my colleague before, we need definitely monitoring systems to get better understanding of the process and to control it and to improve the product and the processes. And here now first, before I go to the examples, you see here where we are looking for, these are the modules we used. It is the ablation systems like milling or drilling. We have also the metal cutting, but then we have also the AM modules, the DED, it's a direct energy deposition. One of you knows it as laser cladding for the repair. And we use also cold spray for the repair. So we have two steps, we have two fields, the manufacturing and the repair. And last but not least, also the process control. As I said, we wanted to have fully control about the process and to optimize the part properties at the end. And now I show you here the modular equipment what we have. We have some elementary modules, means the single steps like the powder deposition or the milling modules, but also a combination between both, so that we use a DED module and combined with a cutting one. And also then the third column, we wanted to bring it into systems like robotic systems or directly in closed machines. And here are the use cases. This is the use case from my company, from Siemens. We wanted to look to the manufacturing and also to the repair of turbine blades or other components. The turbine blades is just an example, but there we have a very complex shape inside, so that means that we have very big efforts, or we have high challenges to fulfill the geometry accuracy, and that is also the tolerances quite high, and we have different kind of spaces. So we have small parts, but we also have big parts up to 300 millimeters or sometimes bigger. So then we have the use cases housing from the colleagues from General Electrics. This is more a bigger part. It's a diameter of 1 meter. So that means the operation systems have to be fulfill the requirements to use to deal with these big parts, and also with the materials, which always are nickel-based alloys, which are also quite complicated to handle. And last but not least, from our colleagues from Globotics, which are running or operating in the oil and gas field. And just give an example for a very big device here that can be in a diameter of 50 meters, so that's really big. That means how can we, that means we have to develop also modules to repair these kind of big parts. And how we want to do, and something about the results that we will now present by my colleague Harry.
Thank you, Martin. Thanks for the very nice introduction to the project and also to the use cases that we have to deal with. As you realized by now, the cases are quite different in nature, and that means that we had, before even start working, we had to identify all the challenges and see where we should intervene. So the first step was to go through, analyze the different requirements of the different tasks and validate a series of opportunities that could arise by using additive manufacturing, but also in combination with subtractive manufacturing for these specific cases. Going through that analysis, we saw that additive manufacturing is quite promising, not only for building new parts, as mostly presented here, but also for repairing and for repairing into the field. And through that analysis, we realized that also the business models of these companies could work very well with on-site repairs of certain components. That allowed us that led us actually to generate these maps that you see behind me, which actually depict the whole process from start to end for all three cases. and then consolidating those to what we call a user meta map. Actually, you cannot see much on the slide, but this depicts everything that has been required for all 3 use cases combined into one. Also in terms of opportunities at the bottom, but also in terms of the digital aspect of things and how we are going to digitally manage this whole operation. The first step towards realizing a solution would be the the design and creation of what we call the co-engineering platform. The co-engineering platform is actually a piece of software trying to cover the whole process chain, starting from realizing that a certain maintenance task needs to be carried out and going on to specifying tasks for the operators and also specifying having a communication channel between the operators and the supervisors. So the first step is what we see here as the main administration dashboard. Back in the factory, someone defines the tasks that need to be carried out. And they define the jobs, which are typically scheduled beforehand, and they define also a list of events and things, checkpoints, let's say, for the operator. And you can see here how this whole thing is being handled. Then this whole information is being transferred to the operator, which views the tasks that he has in hand. He knows, therefore, which areas of the machine needs to be checked, and he comes up with a series of inspections that he has to do. The platform guides him through each one of those steps, and the findings are reported back so that the engineering team back on the factory can check it. And of course, this is also accompanied by certain CAD files. So for instance, here we have envisioned that the operator might be able to 3D scan a turbine blade, for instance, and get that information back to the factory to see if a repair process should be done. And then, of course, it can be decided if that repair process makes sense to be done on site or if they have to transfer these parts back to the factory. For some cases, this is doable. For some other cases, like the Globotics case that Martin presented before, it's not really feasible to move them, so the repair has to be done on site. Then we move on to the repair process. One of the core things is the direct energy deposition process, where we try to start from a mathematical model, implement that in MATLAB, and then integrate that in C++ in order to be able to simulate how the deposition is being made on plates and on the substrates. Of course, having a simulation model doesn't mean anything by itself. We need to have that validated, and therefore we went on to validate what we found out using 2 different machines. The one is a robot-based solution in one of the partners of the project, and the other one is a CNC-based solution using the same process parameters and using the same material providers in order to make sure that our models can predict with satisfactory accuracy, let's say, the results that we are getting from the physical process. And actually, we also used these experiments to also validate the process window in order to be able to get the results that we want from the process. And this is particularly critical because all 3 sectors that we referred to actually are very strict in terms of certification about their parts. Moving on, this is something that is currently a work in progress. It is regarding the process and the equipment sensing, and it's something very critical because, as mentioned, we are going to operate a lot in field, and that means that we have a lot of disturbances from the environment. That means that we should very closely control the process and monitor the process in order to make sure that our results and the outcomes in terms of quality are the ones that we want. So at the moment, we are actually trying to implement the systems to monitor the beam shape and the melt pool shape, and actually be able to correlate the things that we get from the sensors to the product quality. That would be all also from my side. Hopefully we will be back next year to present some more results. Keep in mind that the project is now during its midpoint, more or less, so we hope to have more results soon. You can learn more by visiting our website, and thank you very much for your attention. Are there any questions? So thank you.